had a wave and there was nothing in the way, so like if it went out a window, then that energy just started going and it kept traveling forever and ever and never came back. But you also saw at another point that when you had a wave and it was traveling along and it hit something solid like a wrench or a wall, then it was reflected and it ended up coming back along that bottom, and as it did that, we'll start to get different things that we call interference. So we're going to have two different types of interference that we'll deal with. We're going to be looking at what we call constructive interference. If I think of things like constructive or construction, what generally happens when things get constructed? You think I'm going to end up with bigger waves or smaller waves? Bigger waves, okay? So we can end up with these constructive interference or bigger waves, and we'll also have a type of interference called destructive interference. What does that make you think of? Getting smaller, I'm destroying it, okay? And so what will happen is if I create a wave where I have a crest and a trough that intersect with each other, do you think they're going to build on each other or destroy each other? Build? Alright, so what if I had like a hole in the ground and I had a pile of sand? Okay? So if I take my pile of sand and I bring it closer and closer to this hole in the ground, what happens as it slides over? It's gonna fall. It's gonna fall. It's gonna start to fill it in. Okay? So when that crest comes in and meets that trough, they essentially fill in with each other, and so this would be an example of having destructive interference. I might have two waves, and then they're gonna cancel each other out. One wave's on top and one wave's on bottom, and they cancel each other. Now it doesn't mean that they stay canceled forever. Waves are just energy, so if I let it keep going for a little bit longer, that crest comes right back, the trough comes right back, and they just keep moving on their way. So at the beach, if you go to the beach, you'll see that there's swells. So sometimes the waves get bigger and bigger, and that's that constructive interference. And other times they start to destroy each other, and so then I've got these kind of lull periods between those swells where my waves aren't very big. So if I have a crest and a trough, that's going to be a good example of having destructive interference. So if I wanted to have constructive interference, I would probably need to have two crests. So if I have a crest, and they start to meet each other, it's like having two piles of sand. As they get together, they form one really tall wave. And then again, once they don't stay stuck that way, they just continue to move on. And so this can happen with waves at the beach, it can happen with sand. Music-wise, if I have 2 or 3 people playing the same note and everyone's in tune, they can start to produce constructive interference and sound louder. It will sound like there's more than 2 or 3 people there. It can sound like 10. If someone's just a little out of tune, then you start to hear what we refer to as beats in science, where it kind of warbles. You'll hear it get a little louder and then it kind of gets softer and louder and softer. It's the idea of tuning your instrument. So by seeing those differences, what you're really hearing is times where you've built on those waves, where we're getting closer to having that same sound, and then we'll get a little bit softer, and that's times where we start to destroy each other. So a little bit out of tune creates this same impact of something that we can hear. Today we're going to use a string to kind of represent some of these different aspects. So I've got a speaker over here, and what speakers do is they just vibrate. So as it bounces up and down, it will shake the string. And this frequency generator, this box, is how I'll be able to control the speaker and tell it how quickly I want it to vibrate up and down. And so if I let it vibrate at any random frequency, then I'll get times where I'll have constructive interference, I'll get times where I have destructive interference, and the waves will kind of come and go. But eventually I'm going to find very specific locations where those two crests or troughs, they're always going to find the same spot over and over and over again. And so then it won't look like the wave is coming and going, it's going to look like the wave just kind of stands in place. So when I first turn it on, I've got the speaker just vibrating very, very slowly. And you can see the string just kind of starting to shake. Nothing interesting happens. So you can hear the speaker start to vibrate quicker as I turn up the frequency. And so then you can see where if I let it sit for a second, you'll see times where it looks like this part starts to move a little bit more. And over here, it kind of moves a little more, and then it goes away for a second. It moves a little more, and it goes away for a second. Okay. If this was multiple instruments, essentially, we would have that same idea of you'd hear a slight rise in the volume, and then you'd hear a lower volume, and then rise and then lower. And so within that, I'm getting close to a point where I can create these standing waves, but I'm not quite there. I'm just a little bit out of tune, so to speak. Dial up a little further. Oh, wow. And so then I can find this location where now it's a pretty it's going to stay there. Okay? It's a stable wave. It's not going to come and go. And I'll have these sections that move quite a bit. I got 3 of those sections that move quite a bit. This is going to be a vocabulary word you'll need to know. It's called an antinodes. Okay, so antinodes are these big sections, and they have a lot of amplitude, is the way that I like to remember. And then I've got these sections that don't really move very much. There's no wave forming there, and that's actually what we call a node. Anybody ever seen Pitch Perfect? Yeah. Just admit it. It's guilty pleasure. We've all done it, right? Alright. So Pitch Perfect, they refer to like vocal cords. She had nodes on her vocal cords. Kind of ruined her singing career. Okay. So nodes mean that things don't vibrate. Okay. So here we have a node on a string where the string is not vibrating as much as it is here. That can happen in our vocal cords. So if we develop these little nodules or nodes, it stops our vocal cords from vibrating the way that they're intended to, which definitely makes it very hard to tune in and sing the specific notes that you want to sing. Okay. So here I've got energy happening, which means if I try to touch over here, I kill my wave. But these nodes, they don't vibrate very much on their own anyway. So if I come put my finger on the node there, the energy is able to keep going. So the wave on that side or on this side of me is able to continue. Now it looks like there's more than one string here, but you saw what we started with. There's only one string. So essentially what we're seeing is the string's moving too fast for our brains to understand. And the only way your brain can figure that out is to just start to figure in that there's more than one string there. So what's really happening is the string's going to create a wave and vibrate one way, but very quickly it's creating a reflection. And so since it's going back and forth in both directions, it trips out your head a little bit, and you start to see it as multiple layers of a string. It's hard to actually focus in. Now you can kind of get a little strobe light effect, so as long as you are not epileptic or anything else along those lines, if you look at the string and you blink pretty rapidly, you can actually kind of get little freeze frame images, and that allows you to see there's only a single string there. Don't do it too long, it will give you a headache, but it's a nice little trial.
I'll have an epileptic.
Yes, you can stare at an area, blink quickly, and it breaks it up. So it's like taking a movie and breaking it into individual frames, and you can start to see all the little areas.
I don't see it.
Okay.
Alright. So a couple other things that we need to know. So I mentioned some vocabulary words, antinodes and nodes. I mentioned that we essentially have waves going one way and then reflecting back. So if I could imagine this little freeze frame in my head, as my speaker goes up, I'm going to have a crest, and then when I get to this middle section, it would be like a trough, and then I have another crest again. How many waves would that be? One crest, trough, one crest again. So 3? 1.5. Okay. So I have one crest and one trough, that's 1, and then I have just a crest, that'd be 1.5. But it's got to bounce backwards. So if I have 1.5 going one way and 1.5 coming back, how many waves do we really have? We really have 3 waves. Okay. So one of the nice things about standing waves is if we just figure out how many of these bubbles, what do I call those bubbly parts? Amplitude, antinodes. Okay, if I just count them, that's the number of waves I have. So I've got 1, 2, 3, and that's my waves. Because essentially, if I broke my string into pieces, I'd have a crest going to this spot and a trough reflecting back. Alright, so we have 3 waves, or 3 antinodes. How many nodes do y'all think we have on our string?
2. Not 4.
1, 2, 4. Why 4? On the sides. This is a knot over here, right? Is it moving very much? Not. So that definitely counts as a node. Okay, same thing over here. I've got it tied to that speaker. So the endpoints also counts as nodes, and we want to remember them. Okay, so I have 4 nodes. I have 3 antinodes. And so I'm gonna see if I can't figure out how to get a few more waves on here. Make my speaker go faster. Get close, not quite there. I can make it faster.
It looks like it's
That's pretty good. Okay, oh, now it's going away.
Wow, it's cool.
Down a little bit. Let's see. Let's see what happens if I... So you can hear it moving faster, so that means our frequency is getting bigger or higher. Good. And we start getting... So as my frequency goes up, what's happening to my string here? I got more antinodes and nodes. So my frequency is increasing, which means my number of waves is going to increase. How many do we got? 5 waves? Alright, let's see how many we can make.
Make it bigger.
Oh, wow.
It looks like a DNA strand.
That's pretty cool.
Use a DNA strand. You don't know what DNA is?
It's like DNA double helix right here, right?
Oh, sorry, I just said that. I just said that, huh? Okay.
Alright, so yeah, as this gets faster, it's the blinking part, so someone's saying that they're trying to blink, it's not going to work very effectively when it starts moving fast. Yeah. But we do have several waves here. How many waves do y'all think? 7. Alright, 1, 2, 3, 4, 5, 6, and 7. Okay, which means how many nodes?
That's like a hologram.
9? Alright, count with me. 1,
3, 4, 5, 6, 7, 8.
9? Where's number 9?
Damn.
Okay, just 8. So there's only going to be 1 extra node than there is antinodes. Alright, so as that frequency is increasing, you can hear the speaker go faster. Okay, you can see that we're getting more waves. In order to fit more and more waves on this string, what's happening to my wave length? So the sideways amount of space that this antinode takes up?
Being smaller.
It's being smaller. So frequency is increasing, wavelength is decreasing. What kind of relationship do we call that?
Direct.
Inverse. Okay, direct meaning same, inverse meaning opposite. Alright, let's see what else we can do. How good is metallic? Can you find out?
Oh my god. Oh, now it's not even moving. That's so crazy.
That one's getting bigger, but that one now looks like it's drifting away.
I can do better.
Looks like it's fading away. It's getting thinner. It's pretty cool.
Alright, so the other thing you see is as we get more waves on the string this way, I don't have that much space. So I have to start shrinking my waves in terms of their amplitude because I'm using that energy here as opposed to here. Okay? So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Alright, I got 12. Which means how many notes? 13 notes, okay. Alright. And so if I keep going, then we start getting into ranges that are actually audible. Okay? But if you can hear it, then it's probably past the level of what we can see. Because you don't see the volume of the sound that's coming out of my mouth. So you see low frequency things. You hear high frequency things.
I still see it though.
And when we really want to annoy you,
I'm about it. I'm about it. I'm about it.
you want a hearing test here? Well, let's have a hearing.
Oh no. No. Oh, I hear it. It's funny.
Bet.
I can kind of
Do it.
It's like ASMR.
This is in that most high school students should be hearing this. This is in that mosquito ringtone range. And as you get older, you'll start to lose some of that higher frequency stuff. You should definitely hear this. And if you don't hear this, you should probably go get a hearing test by a real doctor and figure out what's wrong with you. Yes, sir.
Miss, you know how dogs can hear like sounds that we can't hear?
Mm-hmm.
Would they be able to see that?
Dogs actually have pretty poor vision, all said and done by comparison,
Oh.
and that's where having the hearing helps out sometimes, okay? Are there animals that can see faster frequencies than us? Yes.
Lions. Lions is one of them.
Yeah.
Like what?
Like I said, so yeah, if you couldn't hear some of that stuff, probably should get checked out. Alright, now, you've also been doing some math recently, okay? And so, in terms of math, one of your equations has been frequency and wavelength. So I can figure out the frequency. I've got a little digital reader over here that tells me that. Okay. How could I maybe figure out the length of one of these waves if I wanted to figure out how fast this string is traveling? What do you think I could do? Yeah. So paint on it and rule. So a ruler. Okay, what would you?
Divide the string.
Okay. Divide the string up. All right. Well. Because so, how would I divide my string? How many waves do we have right now? 2. Yeah, so if I told you this string was 10 feet long, how long would one wave be? 5. We just cut it in half. Yeah. If I go and I find a different one, how many waves do I have right now? 7 waves. Still 10-foot long string. What would I do? 10 divided by 7, that's a calculated thing, right? Alright, but we can do that, yeah? So I can know the wavelength, I can read a frequency, and that would allow me to get some different values there, okay? I could actually figure out how quickly this string is moving up and down, okay, in terms of getting some relative actions there. Alright, so I'm gonna dial this up, I'm gonna put a relatively good number of waves on here, and then I'm gonna let y'all, if anyone wants to come up and play for a second, kind of touch the different areas of that stuff. Give you a couple of minutes to touch, play, mess with it, whatever. So again, you should be able to touch our nodes because they don't vibrate very much on their own. If you try to touch the antinode, you're going to take away everybody else's fun, but you're welcome to it. And you cannot